Power factor is a measure of how effectively electrical power is being used. A power factor of 1.0, or unity, indicates that all the power supplied is being used to perform useful work. A power factor of less than 1.0 indicates that some of the power is being wasted. A low power factor can result in increased energy costs, overloaded equipment, and voltage drops. Induction motors, like those used in chillers, are a common source of low power factor because they require reactive power to establish a magnetic field in addition to real power to do work. There are two main approaches to power factor correction: firstly, correcting the power factor at individual loads such as chillers, or secondly, correcting the power factor for the entire building at the main service. Correcting at the individual load involves installing power factor correction capacitors directly at the chillers. Correcting at the main service involves installing a capacitor bank at the main electrical service entrance for the building. There are advantages and disadvantages to each approach. Correcting at the individual load offers several benefits. Firstly, it reduces the current flowing through the conductors feeding the chillers, which can reduce I²R losses, that is, current square times resistance in the wiring. Secondly, it improves voltage regulation at the chillers, which can improve their performance. Thirdly, it reduces the load on the utility system, which can help to improve overall grid stability. However, correcting at the individual load can be more expensive than correcting at the main service, especially if there are many chillers to correct. Correcting at the main service also offers several benefits. Firstly, it is generally less expensive than correcting at the individual load, especially for multiple loads. Secondly, it is easier to install and maintain. Thirdly, it can improve the power factor for the entire building, not just the chillers. However, correcting at the main service does not reduce the current flowing through the conductors feeding the chillers, so it does not reduce I²R losses in those conductors. Also, it may not improve voltage regulation at the chillers as much as correcting at the individual load. To determine which approach is best, you need to consider several factors, including the number and size of the chillers, the existing power factor, the desired power factor, the cost of each approach, and the available space. Since the existing power factor is 74, it's significantly below an optimal level, suggesting a considerable amount of reactive power is being drawn. Here's a detailed approach to determining the best solution and sizing a capacitor bank. Firstly, conduct a detailed load analysis. This involves measuring or estimating the real power, measured in kilowatts, and reactive power, measured in kilovoltamps reactive, demand of the entire facility with a particular focus on the chillers. A power quality analyzer can be used to measure these parameters over a period of time to capture variations in load. Secondly, determine the target power factor. Utilities often impose penalties for low power factor, typically targeting a power factor of 0.95 or higher. Determine the utility's requirements and set the target accordingly. Thirdly, calculate the required reactive power compensation. This calculation determines the size of the capacitor bank needed to raise the power factor from the existing level to the target level. The formula is as follows: kilovolt amps reactive corrected equals kilowatts times the tangent of the initial angle minus the tangent of the target angle, where the angle is the arc cosine of the power factor. For example, if the total building kilowatts demand is 500 kilowatts, the existing power factor is 74 and the target power factor is 95, then the initial angle is the arc cosine of 74, which is 42.27 degrees, and the target angle is the arc cosine of 95, which is 18.19 degrees. The tangent of 42.27 degrees is 909, and the tangent of 18.19 degrees is 329. Therefore, kilovolt amps reactive corrected equals 500 kilowatts times 909 minus 329, which equals 290 kilovolt amps reactive. This means that a capacitor bank of approximately 290 kilovolt amps reactive is needed to correct the power factor to 95. Fourthly, consider individual chiller correction. Calculate the kilovolt amps reactive needed for each chiller individually to bring its power factor close to unity, say 0.98. The formula is the same as above, but applied to each chiller's kilowatt and power factor. Then compare the cost of individual correction to the cost of a central capacitor bank. Consider the benefits of reduced losses in the chiller feeders with individual correction. Fifthly, evaluate capacitor bank options. Capacitor banks are available in fixed and automatic configurations. Fixed capacitor banks provide a constant amount of reactive power compensation. Automatic capacitor banks adjust the amount of compensation based on the load demand. Automatic capacitor banks are more expensive but provide more precise control and avoid overcorrection, which can lead to leading power factor and other problems. Sixthly, consider harmonic distortion. Power factor correction capacitors can amplify harmonic currents present in the electrical system. Harmonic currents are generated by nonlinear loads, such as variable frequency drives and electronic equipment. High levels of harmonic distortion can damage equipment and interfere with the operation of sensitive electronics. If there are significant harmonic currents present, it may be necessary to install harmonic filters in conjunction with the capacitor bank. A harmonic study should be performed to assess the levels of harmonic distortion and determine the appropriate filtering requirements. Seventhly, determine the capacitor bank location. If a single, central capacitor bank is chosen, install it at the main service entrance, as close as possible to the main distribution board. This minimizes losses in the distribution system. Eighthly, specify capacitor bank components. Specify high-quality capacitors designed for power factor correction applications. The capacitor should be rated for the system voltage and frequency and should be capable of withstanding the expected harmonic current. Also, specify appropriate protection devices such as fuses or circuit breakers to protect the capacitor bank from overcurrents and short circuits. Ninthly, consider future expansion. Design the power factor correction system with future expansion in mind. The load demand of the school may increase over time, so it is important to select a capacitor bank that can be easily upgraded or expanded. This may involve selecting a modular capacitor bank that can be expanded by adding additional capacitor modules. Tenthly, consult with an electrical engineer. Power factor correction is a complex topic, and it is important to consult with a qualified electrical engineer to ensure that the system is properly designed and installed. The engineer can perform a detailed load analysis, calculate the required reactive power compensation, evaluate capacitor bank options, and specify the appropriate components. They can also ensure that the system complies with all applicable codes and standards. In the case of the high school, given the presence of large chillers, a hybrid approach may be optimal. Firstly, install individual power factor correction at each chiller to address the immediate reactive power demand of these large motors and reduce losses in their dedicated feeders. Secondly, install a centrally located automatic capacitor bank at the main service entrance to fine-tune the overall building power factor and compensate for other loads. This approach provides the benefits of both individual and central correction. The size of the capacitor bank should be determined based on the total building load, taking into account the correction already provided at the chillers. When sizing the capacitor bank, consider the following factors. Firstly, the total kilowatt demand of the building. Secondly, the existing power factor. Thirdly, the target power factor. Fourthly, the harmonic distortion levels. Fifthly, the future expansion requirements. The capacitor bank should be sized to provide sufficient reactive power compensation to raise the power factor to the target level under all operating conditions. It should also be capable of withstanding the expected harmonic currents without overheating or failing. The capacitor bank should be installed in a location that is easily accessible for maintenance and that provides adequate ventilation. It should also be protected from the elements such as rain and snow. The capacitor bank should be connected to the electrical system through a dedicated circuit breaker or fuse disconnect switch. The circuit breaker or switch should be sized to handle the full load current of the capacitor bank. The capacitor bank should be grounded in accordance with all applicable codes and standards. The grounding system should be designed to minimize the risk of electrical shock and to prevent the buildup of static electricity. The capacitor bank should be inspected and maintained regularly to ensure that it is operating properly. The capacitors should be checked for signs of damage or deterioration. The connections should be tightened to prevent loose connections. The cooling fan should be cleaned to ensure adequate ventilation. The capacitor bank should be tested periodically to verify that it is providing the correct amount of reactive power compensation. Power factor correction is an important aspect of electrical system design. By improving the power factor, you can reduce energy costs, improve equipment performance, and enhance grid stability. It's always best to consult with a qualified electrical engineer to determine the most appropriate power factor correction solution for your specific application. In northern Illinois, where the conditions can impact the load on chillers, therefore the design should account for seasonal variations in power demand.